All right. Thank you very much, everyone. Welcome to week 3 of NodeUp Syndicates program. So, this week we'll be talking about smart contracts and EVMs. I'm so happy to be here. I don't know if you're happy to be here. Week 1 and 2 were amazing. Amarachi did an excellent job. She broke down blockchain in a way that I self could not imagine, right? So, whether you're watching on YouTube, you're watching on LinkedIn, anywhere you're watching us, thank you and welcome to week 3. I can see that we have around about 5 or 6 people live. So, what I need you guys to do, for those of you that are live, what I need you guys to do is to first of all copy the link to this live stream anywhere you are watching. First of all, click the share button, copy the link, and then share on your WhatsApp status. Is going to get help more people to get visibility. Then, if you are part of this program and you are part of our community, I want you to quickly copy the link to wherever you are streaming, LinkedIn on YouTube. Go on the community channel and drop that link. It's going to remind other people that this session have started and they should be here, right? So thank you very much as you are doing that. When you do that, kindly drop a comment so we know that you've done that. So when you done that, just type yes or done. Type done on the chat. I'm going to see it and I'm going to give you a shout out. Yeah, I can see more people are joining. Thank you very much, everyone. So our speaker for today is Kemzi. he's um, he's a blockchain engineer, and he's a fantastic blockchain engineer. He will be teaching us today. I mean, for those that are part of this session, you already have the KZ, you already have the details. So Kazeem Olaniyi is a blockchain developer, an excellent blockchain developer, and today he'll be teaching us about smart contracts and EVM. So for those of you that are not part of the program, I'm sorry you can't join again. For those that are part of the program, this is another session for us, and it's going to be a very interesting one. By my time is 5:03. I would like us to start by 5:05. So please, I want to see about 20 to 30 people on this live stream by 5:05. Please kindly remind those that are not part of the program can join. So please still do share with them. Thank you, Kingsley Zikora. Kingsley, we need to give you something. You are very consistent. You're always the first person to show up for every session. You really deserve something in this program. You really deserve something. We need to get you something. Right. So thank you. More people are joining. Thank you. Okay. All right. I can see that people are active on the group chat. So who is yet to we don't enter no door? Yes, of course. So who is yet to submit the assignment? If you're yet to submit your assignment, kindly submit your assignment. Kindly, we are begging you, please. Have mercy on us and submit your assignment. So yeah, it's going to help us a lot. It's going to help us to make sure that you are learning what they are teaching you. About 20 people have submitted the assignment for week 1, and for week 2, we don't have a lot of people that have submitted the assignment. So please kindly submit your assignment, your task, and another one will be given today. Thank you, Emmanuel Ernest, for doing the sharing. Thank you so much. Obasoro, please submit. You've not submitted the assignment, Obasoro, sorry. But then we need you to share this link, share it on your WhatsApp, share it on your copy the link, share it everywhere so that people can be part of this session. And Michael too. Yeah. All right. So this is 5:05, exactly 5:05. Hi, Casey. Can you hear me?
Yeah, loud and clear.
Hi, Casey. Are you here? Can you hear me now?
Yeah, loud and clear.
All right. So hi, Casey. I would like you to first introduce yourself. When you introduce yourself, then you go on and start your session. So, guys, if you are here, the voice you are going to hear next is that of KZ. So, KZ, over to you.
Okay. Hi everyone, I'm Kazeem Olaniyi, a blockchain developer. You can call me KZ. I'll be teaching on smart contracts, and EVM in general today. I'm a blockchain developer. I've worked on some some projects. I've contributed to some open source. I've written implemented some standards like account abstraction standards, a modularized version of account abstraction standards, and the likes. You can check me up on Twitter at RealKZ, on LinkedIn as Kazeem Olaniyi, and on Telegram as RealKZ. So for today, just as Precious have said, that this module is on smart contract and EVM. So I'll be sharing my screen now to guide you. It's going to be a practical session. So if you are not with your laptop, ensure you connect with your laptop. If you are connecting with your phone, it would be nice you have your laptop beside you, or preferably connect with your laptop so you can go on as you can continue with the practice, or maybe like you can continue with the practice as we do some practices. Okay, so let me share my screen now. Yeah, I believe my screen is visible to everybody. Yeah, so yeah, in the comment section, let me know if my screen is visible to everybody. I need to know if can you all hear me?
Yes, Casey, we can hear you.
Okay, is my
Yeah,
screen visible over there?
yes, it is. I believe so.
Okay,
Yes, it
okay,
is.
so let's get started. So Module 3, smart contract and EVM. These are the contents we'll be covering for today. The smart contract broad overview with use cases, why we use smart contracts, the language we use in writing smart contracts. We have Solidity, we have Viper, and any other compatible EVM compatible languages. But for this particular module, we'll be covering Solidity basics, since it's like the most popular language used in writing EVM compatible smart contracts, EVM compatible codes. So for the Solidity basics, we'll be covering the basics of Solidity, the primitive types, the control structure, the data structure, EVM and gas optimization, smart contract security, and in everything we'll be demonstrating them with practical example as we move forward. So starting with, I know majority of everybody here are still familiar with blockchain, and when you hear the word smart contract, you kind of feel like, what's the meaning of smart contract? We already know contract as a a a let me put it as, we already know contract as like an a, a kind of written words or written agreements between two parties. That's what contract are. But smart contract is just more like putting it in program, just like they are written program but stored on the blockchain that automatically enforces and execute the terms of an agreement. So it's just like a written agreement, but in this case, it's particular to like blockchain. And this agreement is being executed provided the conditions are met. It's just like a normal contract. If you have a contract between two people, that we have a contract binding our agreements, that provided we stay true and so, everything works fine. If you do this, you collect your money. If you do this, you'll be paid. If you do this, you will not be eliminated. So that's just smart contract. It's not, forget about the word smart in the contract. It's just like you can put it as a virtual contract. So what smart contract does is they eliminate the need for intermediaries, ensuring transparency. There is no third party. Unlike traditional contracts where it is being binded by maybe like lawyer acting as the intermediary kind of, and in some cases maybe like a third party. But this one, everything is stored by mathematical logic. So when you hear the word smart contract, it's not something smart. Your as they saying as people do say that your smart contract is as smart as the writer. So they eliminate the need for intermediaries, ensuring transparency, security, and automation. So one of the key characteristics of, or let's just say the key characteristics of smart contracts are trustless execution. That is, they do not require a third party. The moment these conditions are met, you have your predefined conditions, you have your predefined logics, provided they are met and validated that these people are this person or these people. I'm just using the context of what we are familiar with. So they do not require intermediaries, they do not require third party person. So that's what it means by saying it's trustless execution. You don't need to trust the system. Nobody can, when there's an intermediary, you need to trust the intermediary. When there's a lawyer involved, you need to trust the lawyer. When there's a third party, maybe like a just as we put it, a trustee, like a trusted third party person involved, you need to trust that person. But this one, it's binded by mathematical computation. You don't need to trust anybody. It's just based on blockchain. And I believe in your previous classes, you would have explained blockchain and why it is trustless. So as blockchain itself is trustless, the execution in it are trustless. Immutability. Smart contracts are immutable. Once they are deployed, there's no going back. You cannot redefine it. You cannot do anything to those logics. You cannot change it. Only if you create another smart contract, redeploy another contract using another predefined conditions. But the moment you deploy it, there's no going back. That's it. Transparency. Smart contracts code can be seen just as blockchain is open. The codes in it can be seen by anybody. It can be seen by anybody willing to check up on the contracts, check up on the logic. So you know what you are getting into. Just the same way a normal contract is, everybody involved can see it. But in terms of smart contracts, everybody have access to the contracts. I can check up on any smart contract deployed on chain. I can check it up, read the code, and all. So tamper proof, it means since it is not immutable, nobody can change it. Since it is not immutable, provided there is no bug involved on deployment, nothing can happen to it again. Like it cannot be hacked. Provided there is no bug involved, it cannot be hacked. So those are the key characteristics of smart contracts. And we move to the flow of smart contracts. The flow of smart contract is straightforward. Write your code, you deploy it, interact with it. That is anybody involved with the smart contract. You interact with it and it get executed based on the logic written in the smart contract. Now we'll move to use cases of smart contracts. Smart contracts are mostly used in a situation where you don't require third party, like where there is no need for third party, where you are kind of looking towards people protect, like people censoring you. For an instance now, because because it is used as the word smart contract does not mean it is only based on like agreements per se. For an instance now, smart contracts can be useful in relation to a swap, like a swap. In case, let's say like a centralized exchange, it's like an exchange. A normal exchange will require an intermediary. For an instance now, if I want to buy something from another person, it will require a third party. It will require a third party, that is the third party acting as escrow between two people. With smart contracts, you don't require a third party. So we have decentralized exchanges, we have NFT marketplace, we have Piggy, just as we have, I believe some people on this call are Nigerians, just as we have Piggyverse, you can have something like that, so written in smart contracts. In that case, instead of storing your money with people, when we use Piggyverse, we are trusting those people involved that these people won't they won't do anything with our money. Like they won't crash our money out, or they won't cash out, or they won't scam us. We are trusting them. But with smart contracts, it's just based on logics, following the logics, and any money involved is not going to anybody. At the end of the day, it's just based on logics, no trusting your money to a third party person. So it creates this kind of self-custodial pattern. So that's for smart contracts. Moving forward, we'll be explaining the basics of smart contract. But before I explain the basic of smart contract, let me show how a smart contract looks like. I don't know if anybody here is familiar with. We'll be using Remix as our IDE because we don't want to bug you with we don't want to bug you with the process of spinning up a Foundry environment, but we can do that if there's still time before the end of the class. So Remix is like an IDE where you can write your smart contract code. So here is an example of how a smart contract looks like. It's just like a normal programming language. It's anybody, I believe we are familiar with programming languages. It's just like your normal programming language where you write your functions, and your functions contains your logics. And anybody interested in interacting with it, they interact with a function, or on clicking on a button when you say submit, you are interacting with a function and like. So that's just how a smart contract looks like. So this is how a smart contract looks like. It's just like how JavaScript, TypeScript, and any other languages are. So back to our slide. Now, for the smart contract, just as any other object-oriented programming languages, we have they have their primitive data types, and within the primitive data types, we have the unsigned integers, we have the signed integers, we have the Boolean, we have the address types, we have the string types, we have the low-level binary. Unsigned integers are used for numbering. It's used for integers that are not negative values, just positive values. And it takes in, because the whole architecture of Ethereum or any EVM compatible blockchains is based on hexadecimal, that is ECDSA pattern. Because it is based on ECDSA pattern, every type size, except in some cases, are 32 bytes. That's 256 bits. So unsigned integers can store numbers from 0 up to 2 raised to power 256 minus 1. So you can store as the largest value of number up to 2 raised to power 256. That's like, if you calculate it, that's like 2 raised to power 256. What you get as your answer, you minus it by 1. So those are the numbers an unsigned integer can take in. While signed integer takes in both negative value and positive value. So for signed integer, it takes in negative integers and positive integers. So we have the Boolean. The Boolean takes in true, false. We have the address type. The address type stores address, because we are dealing with blockchain, and address type is of byte 20 because of the address pattern of
Sorry,
Ethereum
hi,
blockchain.
hi.
Then we have the
Sorry.
string type. The string type,
Hi, Casey, can
sorry,
you hear me?
yeah,
Yes, please. Are you sharing
yeah.
code or just sharing your slides? Which one are you sharing?
I'm sharing my slide currently. We'll move towards the code now.
Okay, okay. I was just wondering because someone said she thinks you're not sharing the right screen or something. Okay.
Oh, I'm currently sharing. You can see my slide, right?
Yeah, if you go back to your slides, yes. I was just wondering if you were actually sharing Remix ID or something.
No,
Maybe.
no. I want to explain the necessary types before moving to, because I believe everybody is an absolute beginner. Is
Okay.
that correct?
Yeah, yeah, definitely. Yeah.
Okay, so let's go with this pattern first before explaining it in Remix ID. So those are the primitive data types we have. Now we'll be going to practical demonstration. Here is remix ID. And just as I mentioned earlier, we'll be using remix ID because of how easy it is to use it, instead of, but for like a real life project where you'll be coding, where you'll be writing sophisticated code, you need things like Foundry or others. So let's continue. We'll create a contract and demonstrate these primitive data types, what they store and how they work. So let's create a new file and call it primitive. Let's just call it primitives.so. So every Solidity program or every Solidity contract must have the .so extension. So when we click on it, and starting with every Solidity code, you must state the license type.
Hi, sorry, KZ. Please, can you put your browser on full screen and maybe zoom in a little bit?
How do I do for
Like,
Remy?
just are you on full screen like this?
Okay, this is my full
Yeah,
screen. Let me zoom
yeah.
in
Okay,
this.
thank you,
Is
thank
it
you.
better now?
Very good.
Okay.
Thanks.
So for every Solidity contract, it starts with stating the license, because it has to explain to everybody that this code, anybody can copy it. We have different types of license. We have the MIT, we have the GPL, I think, and we have some, depending on the kind of license you want to give to your code. There are some licenses that prevent plagiarism, like anybody cannot copy the code. If you copy it, that's like a lawsuit, kind of just the normal way a contract is. But this is just beyond the kind of contracts your lawyer writes, binding to people and the likes. So we say SPDS license identifier, and in our case, we can call it MIT. MIT is an open source. So for this, this has like, so we can start Pragma Solidity. We'll be using Solidity version 26 in this case. So what's this error? Invalid SPDS identifier. Is MIT not a valid SPDS? Okay, I'm not meant to add that. So we start by saying Solidity, that's the name of our contract, Solidity primitives. Now we'll be starting with anything declared immediately after the contract are called state variables. They are called state variables. So we'll be starting with how we stated it. We have unsigned integers, so we can just create our unsigned integers, say uint256. So unsigned integers, they have different value. We have uint104. So in order to know the bytes, uint104 now, as in order to know the bytes each uint type contains, you just divide them by 32. So uint104, we have a byte size of 104 divided by 32. So in that case, it will be bytes. It will be around 3 bytes. The same thing goes with uint 112, and so on like that. We have uint 120, you have uint 144, but the most common one that you'll be using uint 16, you'll be using uint 24. Those are like the common one. Uint 32, uint 256, uint 40. Those are like the common one you'll be using. But let's go on. So uint 256, let's call it number. Let's call it positive integer. I know you may feel like, where are we driving at? So let's use int 128, and let's call it integer, just integer. What other? We have boolean, right? Yeah, we have boolean. For our boolean, for our bool, we call it, let's call it condition. auth again. We have address type. This is how you write. So if you are writing a uint, this is how you write it. If you are writing an integer, this is how you write it. It can, depending on the kind of integer you want to write. If you want to write boolean, this is how you write it. Address type. So address type stores your address. You know, when you want to send money or anything that has to do with money, we use address here. It's just like accounting real life. So address, I can call it, let me use Kazeem. Just, I don't want anything. So these ones are just like the variable names. These ones, you can use any names for them. What these ones are like the types for them. So we have string type. String needs to be declared, I think. We have the string type, let's call it str. Then we have the bytes type. So the bytes type we'll be using is a static byte 32, and let's call it my bytes. As we move forward, we'll still understand what these things are for. So for an instance now, let's say I want to create, I'm kind of short on idea. I want to create a counting system. We can say function count. So let's call it, we want to create a counting system. Let me create another contract. I can write another contract within a program. So let's call it contract counter. So for this contract counter, we can use, as we defined it here, uint 256. We'll still talk about the visibility. As you can see, the AI, or the what's it called? The complete assistance declared public. So we'll still talk about this visibility, the public you are seeing. So the uint 256, let's call it counter, yeah. And let's declare it as 0 as the default, like we declared it in this case. If you like, you may not declare it and declare it in a constructor, or you may not declare it and declare it in a function. So what we want to do now is write a smart contract that increases and decreases this counter. So we can call function increase. And what this function increase does, this function now, that will take me to explaining solidity function. So solidity functions are block of codes. They are just block of codes that perform specific tasks within a smart contract. They are mainly for defining logic of contract and allow interaction with Ethereum blockchain. So these functions are like entry to execution. Function is what you interact with. They are like entry to your execution. They are there to modify the state. This one right here, this uint counter, they are state variables that you store in your storage. Anything stored here, it is persistent on the blockchain. That is, it's just like our phone. We have RAM and we have storage. Your RAM can be like 16 gig RAM. Your storage can be like 512 gig. What the RAM is there for is just like a kind of a temporary space, to store, maybe like to store your, I don't know if I'm correct, but that's how it is, like a temporary place to store your app for a while the storage, anything you store in storage, is persistent until you delete them or you modify them. That's exactly what this thing are. The counter here now is a persistent storage. It stores in storage, and anything declared within the function, they are like memory. They are just within the life cycle of that logic, or within the life cycle of the transaction. So now sorry, Solidity functions, they define the logic of the contract. Depending on, that's where you write the logic. Anything you want to do, that's where you write it. That's what the functions are for. And the key features of them is encapsulating of just how you explained the state interaction. As I explained earlier, function is responsible for modifying the states, or interacting, reading the states, or interacting with the state externally. The same thing goes with visibility control. So these functions as visibility controls and custom modifier, such that you can get this function that these are the only people that can interact with this function. These are the only people that can click on, that can interact with the function. Let me use the word interact instead of click. These are the only people that can interact with the function. And the visibility means this function, I only want it to be seen within the scope of this contract, or I want my function to be interacted with from outside another contract. So for this function now, we have function increase. We'll be giving it a visibility, and the visibility comes in four forms. We have the view function, we have the view function, we have the public function, we have the external function, we have the pure function. I did not add those ones here. We have the view function, we have pure function, we have external function, we have public function. So with public function, if I declare this as public, it means they can interact with it. Anybody can interact with it. I feel it's better we just demonstrate it. So let's write our code and say plus equal to 1. And what this one is saying is just like say counter equal to counter. What we are doing here is saying what we are doing here, we want to increase this counter. So we can say this counter, we are calling it here. That is, we want to modify the state of this counter. So we are now saying this counter, give it this value. That is by saying counter, this counter again, the current value of this counter plus 1. It's still the same thing. If you are familiar with TypeScript, JavaScript, or most object-oriented languages, you'll be familiar with this short pattern of saying plus equal to 1. So it's just saying whatever value this counter has, if this counter already have 3 in it, all is just saying that increase the value by 1. By this counter, we want to increase the value of this counter by 1 by adding 1. What this counter is doing here, this is the one receiving the new updated code. This counter is the one reading the current code plus 1. I don't know if I explained that. So let me just move forward. So this is how you write. Let's go with this. We should not go with the second one. It may cause confusion. So with this now, we update the states. Let me return this back to 0. We modify the state variable. That is, we modify the state variable here. So let's write function decrease too. And with this public now, what this public is saying is that we want this function to be called externally, internally. With this function now, let me call this one function decrease. I want to demonstrate something. Let me call it external. External is another form of visibility. With this external visibility, this function decrease can only be called outside. That is, it can only be called from another contract, but it cannot be called within the contract. We'll do some demonstration with that. I said increase as public visibility. It can be called both outside and within the contract. I can call my increase function here within another contract, that is within another function, call it here. It will work fine. Doing it this way, it will work fine, and that's because of the public visibility. But I cannot do the same for function decrease. Let me say I call this decrease. I call this decrease proxy. Let me call it proxy decrease. And let me call it internal. Let me use internal. So that way, I guess would have used the old visibility. We have public visibility, we have external, we have internal. Am I missing any other thing? We have private too. Yeah, we have private. We'll still get there too. So for the Internal now, it means it can only be called within the contract, that is within this particular contract. This contract right here cannot have access to this internal. If we want to use this contract to interact with this contract, the contract here won't see this internal. No, sorry, please. The contract here can see this internal, but it won't see if it inherits this counter contract, but it cannot see visibility called private. Let me call it, let me use this counter suggestion. We have private function, so I'll be explaining this for. I already explained public that it can be called both outside and inside. External, it can only be called from outside. That is when, let's say, this Solidity primitives wants to interact with counter. If it's interaction, it can only interact with this one and this one. But if this contract is inheriting it, I'll still explain what inherit means. If this contract inherits counter, it will have access to every of the code, including the internal functions. While the private means it can only be used within this particular contract. It won't have any contracts that inherit it won't have access to the private functions. Yeah. So moving forward, I think with that I've explained functions visibility. So let's go back to our decrease. Okay, let me use this as illustration, or so time has gone. Let me just demonstrate our counter, and let me call this counter -1. We have it this way. So from this point, we auto compile. We compile. After compiling our code, we deploy. So this deployment now, it's a local deployment. We can deploy locally. When we deploy locally, it is only visible to us. It's just like local development. Nobody will be able to see. It's just like for testing sake, just a normal way you do with deployments, where you have your local deployment, staging, and production. Just the way you have local environment, staging, and production. This one, it's more like your local environment. Any interaction done here, you are not deploying to a testnet. So aside from this, you can deploy to a testnet and you can deploy to a mainnet. A mainnet is more like a production stage. That is, it's where it deals with like real money, kind of. So these are our two contract, that is the counter contract and the Solidity primitives contract. One thing you notice, let me deploy the two. Let me deploy counter first and deploy Solidity primitives. One thing you notice with why is it stored here as storage? Let me delete this. Okay. One thing you notice with these two contracts is that one contract, just as we explained here, you can see, because we stated that this two function visibility should be public and external. Public means it can be interacted with from outside and inside, while external means it can be interacted with only from outside. The way I inserted increase here, that is, I called increase from this decrease function. I cannot do the same for decrease. That is, I cannot say decrease. It will try an error. It won't see it. It won't see it because it can only be called, this one can only be called from outside. So let me clean this up. Because as I explained here, the function, as I explained for function the other time, I said they are they define the logic of the contract and allow interaction with Ethereum's blockchain. So a contract that does not have a function won't you won't even be able to modify the states. You just have the state there, dormant there. That's an illustration of what we have here. As you can see, there's nothing to interact with. There's nothing to call here. There's nothing to do here. It's just like a contract with storage. It's just like having a memory card, and that memory card, you cannot use anything to store on it. You cannot use anything to delete from it. You cannot use anything to modify from it. So this just like functions are just like entry points to modifying the state variables or modifying storage. Now let's go with declaring. Also, the function visibility is not limited to functions. You can use function visibilities in your types too. So I can call this one public, but the default for all types are private. And that's this why we did not see it here. Sorry about that. And that's this why we did not see this counter here. So let's add public here and redeploy. Let's add public here and redeploy. When we do that, this thing is already on auto save and auto compile. It's already at auto compile. You need to set that. If you are using Remix, you need to set it to auto compile. If not, you'll be compiling for every changes. So when we deploy this, what do you notice? We now have 3 buttons here. That is the decrease function, the increase function, and the counter. And as you can see, you see that for Remix, they define this one as orange like button, while this one is more like a bluish. Is that bluish? Yeah, a kind of a bluish button. What this one is saying is that this orange likes button is modifying the states, is modifying a storage, while this one is just like a visibility, a read-only kind of thing. It's just like a read-only kind of thing. So now we have a counter 0. And we said your in256 can only store a positive integer. Sorry, please give me one. Okay, don't worry. We said your in256 can only store positive integer. If we try to decrease it, that is, we try to say is 0 minus 1, that will be minus 1. But because we are using your in256, it won't be possible. And that's because we are using a Solidity version that prevents underflow. Assuming we are using a Solidity version of maybe like anything below is 0.8, maybe you use a Solidity version of 0.7, there will be an underflow. That is, this 0, if you kind of try to decrease, if you kind of try to interact with this decrease function, that will be 0 minus 1. Instead of storing here as minus 1, it will store as the maximum number of your in256. It's just like going back to like the maximum number. I don't know if you get that. So sorry, let me check if there is a question, if there is any question here. Do we have any question? Okay, let's move on. I'm big on time. Let's move on. So now let's interact with this. Okay, let's try to decrease first. And this will illustrate, as you can see, when we try to decrease, we got an error saying the transaction has been reverted. That is, it's not possible. And it's not possible. Assuming we are using a Solidity version, a Solidity version of, let's demonstrate it. Let me see 0.7. Will this thing not shout on us? Let me change the compiler. Okay, the compiler has changed automatically. Let's compile this. Let me delete this. Let me redeploy. So when we redeploy, let's try to call this. I said anything below is 0.8. It's not a safe coding mechanism. It gives you like, instead of putting -1, because your in256 cannot store negative integer, it will go to like the maximum your in256. That is, it's putting it like it's starting from the far right hand side. So let me click on decrease. As you can see, it works here. And if we look at counter, it gives us the largest value of yen 256. That's a big security vulnerability, provided that's not what you are trying to achieve. So those are one of the security consciousness you have to be observant on as a smart contract developer. You also need to have a broad knowledge on security. Nothing much, but the moment you start writing code, you understand what I'm saying. So let's continue with our demonstration. We check up on our counter state variable. It's on counter 0, that is, we've not added anything to it. On clicking on or on interacting with the increase function and check it again, we have the counter increased by 1, and we can interact with decrease to decrease it. So that's just a basic counter. We can do the same with string by using the storage format. I don't know if we should do that. Let's quickly do that. So we can have our contract storage. Our contract storage, we call it string. We call it string public name. So we can have it as a function set name. Yeah, they've suggested for us set name, and our set name. Now, because of the kind of data types that comes with string, while working with string is more like a dynamic data type, unlike all these ones that are more like static. Because the way smart contracts are, if you are working with smart contracts, anything you are doing, any of the state variables you are working on, or any any state variables you are working on, the compiler needs to, or how am I going to put it? The compiler needs to know the size, the data type size you are working with. So for string now, string is more like a dynamic data type. That is, for a string now, you can't really say this is it does not have a fixed data type. I can store, for an instance now, I can store my name as KZ. This KZ now has 6 characters. With these 6 characters, it's currently using like 6 bytes. And this KZ can go as long as having numerous numbers, and even go beyond the normal 32 bytes. So in order to save that, the storage, the layout of, I'll put it as the storage layout that deals with storing string is quite different from how it is for the data types that are static. So we can say we have like static data types and dynamic data types. The same thing goes with array. The same thing goes with bytes. This byte is a fixed byte. The same thing goes with like a dynamic byte. The same thing goes with mapping. So moving forward, let's demonstrate the storage pattern. So here is it. We have, now for this string now, we need to declare the storage pattern we want for this string. If it is, for an instance now, this is a parameter, so we need to declare the storage type we want this string to store as. Because we are dealing with function, we can use memory, and let's use this for it. Close it. Okay. And use the public keyword. So from this now, we can put, okay, let's just put set name, only set name. Now let's quickly deploy it. Time has gone. Now we have storage, because it's on auto compile. We have storage. We deploy it. Now we have the set name. Just as I explained, set name is modifying the state variable. Now if we check up on the name now, the name is empty. Now if I put KZ I interact with set name and check up on the name, now we have cases. So the same thing goes with sorry. The same thing goes with int, boolean, address, string, and bytes 32. So that's the illustration for the integers. In order to understand it
So,
better, you can check up on Solidity by example. Let me drop the, I don't know if I can drop the link.
yeah. Casey, I was thinking if we can talk about EVM,
Yeah,
and gas,
yeah, I'm going there, so it's part of the,
Okay.
but I'm just looking at the time.
Yeah,
I don't know if you can share
yeah, I'll
this
share that.
with them, Solidity by example, so we can save ourselves the time. Now, moving forward, let's move to EVM. Let's move to EVM. So, EVM is just like an operating system within, just, I believe in your previous class, they would have explained how Ethereum works in general, or any other EVM compatible chains. They call it EVM compatible chains because this EVM itself, it's more like an operating, it's a decentralized operating system that it's like it's a decentralized operating system that must be on every client's devices, that is every client's computer. And the work is just to execute smart contracts. That's the work of an EVM. So if you be writing any language, just as we wrote Solidity, Solidity compiles down to, the Solidity smart contract compiles down to bytecode that the EVM understands. So the Solidity itself is like a high level language, and the EVM only understands the low level language, that is the byte. So EVM is a decentralized computing environment that executes smart contracts, and people regard it as the word computer. So it's like a computer, it's let's put it as a word computer. It interacts, it executes our codes just the same way we did for the other time where we increased the state variable. It follows through the process of EVM executing what we actually want to do. Now, the EVM processes, it it reads bytecode. That is, when your contract are deployed, the contract are deployed as EVM bytecodes. Then, let me just use this as an illustration. So this is like the EVM architecture. When your contract are deployed, when your contract are deployed, it is stored here. This is the EVM code. It is stored here as a bytecode, your virtual RAM. And this one is immutable. It means you cannot alter it, you cannot change it. So whenever there's an execution, for an instance, the function increase, when you want to interact with the function increase, the EVM executes it by using this part. What it does is, this stack here is responsible for operations, for a temporary operations. It's a LIFO pattern, that is, it deals with like some opcodes. So opcodes are like the instructions. They are like readable instructions of just like bytecode. They are instructions. They are the necessary, like they are readable instruction. Sorry, I'm a little bit distracted from this outside noise. They are instructions. Sorry, please give me a few seconds.
Sorry about that, guys. Casey will be back in a bit. Um, Precious, are you there? Precious, are you there? Okay, so I'm just going to talk about why we are doing this and why we are actually
Yeah.
okay. Precious is here.
Okay.
Why
Go
DevOps
on. Go on.
engineers want to at least know some things about Solidity, right? You don't have to know anything about Solidity, but as a node ops engineer, it's important to understand the components of what you're deploying, right? You can't be a node ops guy and you've never heard of smart contracts or do not know how the smart contracts function or EVM or how does EVM relate to AWS, for example, and how can you like convert your basic EC2 instance into an Ethereum virtual machine? How do people deploy smart contracts in that virtual machine? How how would the smart contracts interact with the EVM and how the EVM interacts with other nodes that are running EVM also. So this section is actually very, very important because if you know how smart contract works, you kind of have cracked the code in terms of understanding how the blockchain interacts with each other, right? And when you make a transaction, how does it work? What is under the hood doing that? Smart contracts, of course, and the back end. You've heard of dApps, right? So dApps are decentralized application. Precious, please, can you reach out to KZ, maybe in the chat or privately? Yeah, so I think we'll take some
All right.
questions here. Um, can we have the link to Solidity for further studies? Yes, I shared this earlier, Solidity by example. I'm going to share that again. Yep, Solidity by example will show you like some stuff. You don't have to go too deep, but understand how to write a basic smart contract and how to deploy it. Um, okay, I think Casey is back. I'll bring him back on stage, but we have one question. Casey is back. Can we use general purpose codes like Python to do the same work as Solidity? I think there
No,
is
no,
Py,
we can't. Except it depends on if you have a compiler
Py.
that compile Python to a bytecodes, like to the low-level language EVM understands. So you can use any language, provided there's a compiler that compiles it down to a bytecode that the EVM understand.
Casey, are you ready? Should I share your screen or how are we doing it?
Can you hear me? Let me just be sure that
Yes, I can hear you, Casey.
yeah. So let me proceed.
Okay.
I'll proceed with EVM, the EVM continuation on the EVM. So just as I explained earlier, this EVM itself is like your operating system, just the same way your operating system works in your laptop that deals with like execution of codes and storing to your storage using your RAM, using some part as calculation. So you have your virtual RAM that deals with storing of your codes in form of bytecodes. So the bytecodes are stored here, they are immutable. You cannot change it. That's why the moment you deploy it, you cannot change it. Only if you deploy another contract. While this one are what are the things that deals with the execution, like they are the execution. This like is the execution architecture. So whenever there's an interaction, for an instance, the way we want to interact with function increase, the function increase follows the necessary step. The EVM checks up on the opcodes. Opcodes are just like they are low-level machine instructions. They are instructions within bytecodes. Bytecode contains opcodes. So opcodes are like low-level machine instructions that the EVM use. So depending on opcodes, these are like if you want access to all EVM opcodes, this a place you can check up on the opcodes. This is a place you can check up on the opcodes. These are the EVM opcodes after the CanCon upgrades, that is the DEMCON upgrades. These opcodes requires operands, operations, and different forms that the EVM will use to execute any codes. And we have the stack. EVM, they say, is a stack-based machine. That is, for every of these, in order to execute, for an instance, if there's a, let me use what we are familiar with already, that is the storing and loading, storing to this, storing to this place, storing to this storage, like using the state variable to store to storage. So we have an opcode that handles that. We have the store. So this store now takes in the key. It takes in the key and the value. That is where you want it to, the key to the storage, that is where you want to store your variable, where you want to store your value and the value. It's an opcode itself. But because we are dealing with a high level language, a high level language, we don't really need to understand it, but we need to know how it works under the hood, because that particular, all these opcodes and the opcodes are just like the necessary set of instructions that the EVM use to execute your code. So for this our code now, we are telling the EVM in a high level form that we want to store +1, we want to increment our counter by 1, and we want to read, that is for this one, we want to read our counter and so on like that. So that's how the EVM operates. And if you look at it, at the end of the EVM, you see the account storage. This storage is like the persistent storage. They call it the word states. It's anything, any modification done here, because we are working in the local environment, any modification done here, that is any modification done here at it's on the word state storage, or let me just say it's on the storage. And this storage is persistent compared to your memory. The memory lifecycle state is only within the transaction. For an instance now, assuming there's an argument here, okay, we have a function. If we have an argument here, this function name, anything written here will only be alive, or let me use the word life, will only be alive, or will only be visible. That is, the name states here and everything states here. If we have a function, let me say string memory, let me use this. If we have it this way and you call on this set name, this temp is only available during these transactions alone. I guess that explains this better. So you can use illustration. I believe you guys are DevOps engineer. You can use the illustration of our phone, our computer, where you have our RAM, the work of the RAM, the work of the storage, and the work of the operating system itself, how they work hand in hand. That's how EVM operates in general. So that takes us to gas. Because we are dealing with a decentralized machine, we are dealing with a machine that is not centralized to one person, it is not managed by one person. There can be an issue with DOS attack, that is people stressing this machine a lot, like people sending too much of execution, and this EVM won't heal. It will keep on executing it until it can't do the work anymore. Like there's too much of load work, or workload, sorry. There's too much of workload or too much of executions to be executed. Then the EVM can affect the efficiency of the EVM. In order to prevent things like DOS attack or things like overstressing the EVM, for every execution, they now bound every execution by gas. This gas is mainly like the gas, as explained here, is a unit that measures computational work. If you see here, when we want to interact with our, okay, let me explain that before going to it. When we want to interact with our function increase, the program counter counts the numbers of the steps taken to execute that function increase. And for every step, for every opcode has its own gas. If you check up on this EVM codes, you see that they are minimum gas. There are some that has static gas depending on what you are storing. So this gas now is just a unit of competition, is a unit of computational work that you do. So that's what the gas there is for. Is to ensure the safety of EVM, is to ensure people are not overstressing it, is to ensure there is nothing like DOS attack on EVM. So the gas is paid in ETH. So for an instance, this 100 gas now, with this 100 gas, for us to convert it to ETH, we check up on the current gas rate. The current gas rate may be like 1 GUI, and GUI is like the is like 10 raised to power minus 9 of Ethereum. That is, if the current Ethereum is $1,000 for an instance, 1 GUI will be 1,000 times 1,000 times 1 exponential minus 9. So the result you get, you multiply by the minimum gas. So that's the gas requires for this particular one. So in this illustration here, these are some examples on gas cost per operation. For writing to storage, you can use about approximately 20,000 gas. For rewriting to storage, it's not like, it's like an auth, they call it auth auth writing. This one is like a code writing. So you use about 5,000 gas. For reading from storage, this reading from storage won't attract gas until it is being called within like a write function, a function that has to do with modifying a state, then it will be accounted for. So some people do call it a kind of nominal reading from storage. And this one requires things like operands, adding to numbers, multiplications, and the likes, approximately 3 gas. Sending ETH, if I want to send ETH using transfer or just EOA to EOA transfer, it's attract about 21,000 gas. So this gas now is just like a unit that measures computational work, just the same way we have it in real life scenario. Now that I understand that you guys are coming from the DevOps perspective, I'll be using that as an illustration. In a backend system where we have we want to release our, I don't know if I if I put this well, we want to release our backend interaction to the public, like using API. In order not to in order to ensure the safety towards our system in general, we can put in some computational unit to it. That is, we can put in some kind of fee that if you are calling this particular API, it will attract some certain amount of fee, or some people, depending on whatever they want to use for. So if
Sorry,
you
hi,
want to use that,
hi, Kizzy. We're
yeah,
actually conscious of time, so can you
wow, time
please,
has gone.
let's see how we can wrap up. So we can answer questions, because people have a lot of questions.
I
Uh,
wish I can go beyond this. So for the slide will be available, places you can go to understand this better. You can check up on EVM codes to understand the VM. You can check on Solidity by example to understand the Solidity contracts. You can also check, so just type Solidity to understand how Solidity works. And that takes me to like, I won't be able to cover security since before you can work on security, you need to understand smart contract fully. Though I put it down in my module illustration, so you can check them up. So these are like gas optimization strategy. You can check them up by using storage efficiently, utilize state variable packing. I did not explain storage layouts, so you can check up on storage layouts yourself. I know the time is short to cover for all these
uh,
things.
yeah, this is a lot. I mean, the security part. Can you just go back and just explain reentrancy? I think we can
Okay,
have time for that. Reentrancy attack.
so in smart contracts, A smart contract can interact with another contract. And when a smart contract wants to interact with another contract, and the smart contract, or let me just say, reentrancy attack, let me just explain reentrancy attack. Reentrancy attack is like recalling a kind of recursive interaction with a function that has not fully ended. For an instance now, if we are trying to transfer money to an external contract, and we did not handle the state variable well, like we did not handle the storage well, that is the amount the amount the person have. I don't know if they'll get the context, because that's as I just said, I won't be able to explain security because it requires them understanding how smart contracts works. So reentrancy attack is just like of recalling of a function when it has not been when the whole interaction has not ended. I don't know if I explained that well, or you can check it up how they work. Integer underflow and overflow. I explained that during the process of explaining these front running attacks. You can check up on all these attacks. I want you to check up on everything, go more on it. The 1 hour time is not enough to
Yeah.
link closest to all these things. And after that, after checking up on them, you can take up these assessments, write and deploy a basic. You should be able to even do this. This is a basic smart contract on Ethereum. We wrote 2 basic smart contracts, so you can just think of any other thing and write a basic contract based on what we've written so far. And you can always use AI, as AI is here to help you, and we can use that. So let's use the okay, you already dropped re-entrancy attack. Yeah,
Yeah.
so let's go for any questions available. Time has gone
Thank you.
fast.
Thank you so much. Thank you so much, Kazeem. Thank you so
You're
much.
welcome, Precious.
All right. So, guys, I know you always have like a lot of questions in this session. So, let's see what you have. If you have any questions, I know Kame has been doing a good job in the comment section answering a lot of questions while the session
Okay.
was going on. So, yeah, if you have any question, just drop it before we round up. I have question. Kingsley, now drop your questions. I think the thing with these things is that there is no way. Okay, there's a question on the screen. Emmanuel next. How does storage collision risk? How does storage collision risk emerge in upgradable contracts?
Okay, before you understand storage collision, you need to understand storage layout in smart contracts. Storage layout in smart contracts, for the state variables we declared here, they are stored in every state variables. You know, I explained that every storage has its own slots. That is, smart contract has is 0 to 2 raised to power 256 slots. If you are storing anything to a storage, you are assigned those slots. So if you assign two variables, or if you assign two different stuffs to the same slot, there'll be a collision. Especially if they are not of the same type, there'll be a collision, and that's a big vulnerability in upgradable contracts. So that's the context of it. Does every
Right?
application built in
Yeah.
Ethereum use the EVM? Yes, the EVM is just like your operating system of your phone. It handles the execution of your smart contracts. How were they deployed before the EVM? The EVM is part of Ethereum. EVM is part of Ethereum. It's built with Ethereum. Bitcoin does not have any operating system that handles the execution of smart contract. That's why it's not possible with Bitcoin. That's why it's possible to write a smart contract with Ethereum. How will application be built before there is Ethereum, or is EVM as old as Ethereum? So yeah, EVM is built along with Ethereum. Any other question?
Questions.
What
I think we
IDE
have
should we install?
should
For
we
now,
install.
you can
Yeah.
continue with using the Remix IDE, but if you want to go, big, like you want to write a full code that, because after writing a code, you need to check up on the security part. Then Foundry is necessary, ADAT is necessary. What would happen if a contract recursively called itself once it gas run out? It will keep depending on the logic written. If the logic for an instance, let's say in a gaming situation where the logic increase your points, if instead of the logic to only be called once, if there is a vulnerability and the logic keeps calling himself, the game will be manipulated such that it will give you a point that is not meant to be that is not meant to give you. So instead of giving you 10, you keep calling it, then it can give you like 1,000. The same thing goes with like with money withdrawal. If you have a withdraw function, instead of the withdraw taking like instead of the withdrawing once, and there's like a reentrancy vulnerability there, it will keep withdrawing that you can even remove the old money in the smart contract. That's a big vulnerability, and it's really, really common at some points in the Web3 space. Kingsley, you're welcome. Since EVM code is immutable after deployment, how does upgradability works under the hood? Does it violate the EVM's design principle? No. Upgradability works with proxy design. It works with delegate call. So delegate call is more like you having a contract that delegates call to another contract. Before you understand that, you can check up on delegate call. So nothing changed. Everything you deploy is still within the EVM. It is immutable. So it's just like when you want to upgrade to another contract, you are now delegate calling to another implementation. So that's how upgradable contract works. What are the advantages and disadvantages of using smart contracts compared to traditional system? Just as I explained earlier, there is no third party involved. It is basically calculation, logics, nothing more. No third party involved. With traditional system, you require a third party. Like for a traditional system, they can censor it. For an instance, now when we talk about banks, you can deposit money. Let's say you can deposit 100,000 to your bank account, and it won't reflect until you go to bank to complain. That case cannot happen with a smart contract. Provided everything falls into place, you don't have any problem. Could the EVM's architecture support parallel execution like Solana's runtime? That's in view for EVM. EVM, it's not really based on parallel execution, though some L2 supports parallel execution, L2s like Stacknet and the likes. So I think that'll be the end of answering questions.
Okay, there's
Yeah, I was going
any
to
other
add.
question? Okay, okay, man, go
Sorry,
on.
I was going to add to this question. This one, advantages of using smart contracts. Let's just say blockchain in general. Immutability too is also there. I mean, if you put something on chain, I mean, there are ways to actually, update those files. I think with upgradable contracts, but if you put something on chain, it's actually there on chain, and it's actually visible. So the data is actually distributed to different nodes or different machines running that particular blockchain, and it's very transparent. Anybody can go on a explorer to see the contracts that you are using, to know if it's vulnerable or not, or to even see the transactions that has been going on. So that was to answer this question, the advantage of using smart contracts compared to traditional systems.
Yeah, thanks for that. How does
There's another
EVM
question though.
and gas?
How does
I,
EVM?
I I thought I explained that already. Gas and gas limit doing transaction processing. Every transaction has its own gas limit ensure just as I explained earlier, every transaction has a gas limit, and the moment you go beyond that gas limit, the transaction won't go through. If what you are trying to execute goes beyond the gas limit, the transaction won't go through. Yeah, please do, Emmanuel. Please do. Yeah, I think
All
that's
right.
enough.
Thank you very
This what
much. Thank you very much, everyone, for asking those questions. Okay, I think there's one last question.
Yeah, smart contract can be used. I'm currently working on a project that we are using fiat, like we are creating an FX marketplace, like FX exchange, instead of the traditional FX market that is 245, that is 24 hours, 5 days. So we are currently working on a project that handles that. So
Yeah, yeah.
it's to just
So
replace this.
I'm going to add to that. Like, smart contracts is not just for cryptocurrencies. Or you can use it to write a voting system. You
Yeah.
can use it to create a gaming system. You can use it for anything, basically. You get, so it's not only
Anything
for,
that will require third party inputs.
yes, yes. You don't need a third party. You can, people create a whole organizations out of just smart contracts. That's what they call DAOs, Abi, decentralized autonomous organizations.
Yeah.
So yeah,
There's another question.
I
I'm
explained
curious.
the
What are
I
the steps
explained
to
the
deploy smart?
steps. Okay, you can check up on the steps yourself. Check up on
Yeah,
found documentation.
because I think that's also part
yeah.
of the assignments.
Deploying smart contracts on Ethereum. I think that's the assignment. Yeah,
Yeah.
that's the assignment.
All
So
right.
there are documentations to actually do that. So I will share that documentation with you. If Casey has it, he can also share.
Okay,
Yeah.
let me see. Foundry documentation. Oh, let me drop it here.
Yep, yep. EVMs can be installed like traditional AMIs. That's like, I won't call them AMIs because it's not. AMI actually means an Amazon machine image. So an EVM can also be a binary or just an image you can download using Docker, right? And like install and set it up on any virtual machine. You know, yeah. So it actually would have like an image if you're using Docker to set the node up.
Emmanuel, I will still asking questions. Time has gone already. This is 23. We are 23 minutes
Yeah,
above
we
the.
are 30 minutes past the. Yeah. So, all right. Thank you very much, everyone. Okay, you still want us to take some more questions? Think we've. See, Emmanuel, no more questions,
Well,
please. Thank you.
yeah, yeah,
But did we answer this one? So EVMs are available to install like traditional.
yeah. We did.
Yeah,
I think.
okay, me already
Yeah.
do
All
that.
right. Okay. Thank you very much, everyone. Thank you very much, Emmanuel. Thank you very much. We didn't even have time to exhaust everything that we have for today. Maybe we'll find a way to bring Kazim back or something.
Yeah, Kazim is coming
So
back next week.
he'll be
Kazim
back
is coming
next week.
back.
Just that next
Yeah.
week he'll be taking something else now to be another topic. So
Yeah, I wanted to
but
talk about that next week. Like, you don't want to miss next week because it's kind of like the practical side of things, like setting up wallets, MetaMask, testnets, getting faucets. So we've been talking theory since now we have to start using the blockchain, right? So to be in this industry, you have to be using the tools and using the blockchain. It's not just knowing these things, it's about using it. So next week come, we'll be using MetaMask, talking about wallets, we'll be getting faucets and how you can get faucets. KZ is actually ready for that.
all right. So don't miss next week. Don't miss next week. Right. Okay, thank you very much everyone for joining, spending 1 hour 25 minutes with us. Thank you very much. See you guys next week. The link for your submissions, remember the assignment we gave for this week. The link for the submission link will be shared. The submission link will be shared. Please try to do the assignment. It's going to help you also have some things ahead for next week. Right. So yeah. Um so we've shared the slide, the what's it called? The curriculum with you. Check the welcome email that you got. You're going to see everything that you need there. Samuel. All right. So thank you very much, everyone. Thank you very much, Kazim. Thank you, Kame. See you guys next week. See you guys next week.